Today we have the presentation from Professor Zheng-Tong from Southampton University. He is an expert on fluid flow simulation inside the urban canopy. So he works a lot. He has lots of published work in this subject, especially in large-eddy simulation. So we are talking with one of the best researchers in the area, and he has some really good new developments in the field of thermal stratification, which is a particular interest for us Brazilians, since we work with a lot with under unstable and very unstable conditions here in Brazil, right, because of the weather. So, Professor Zheng-Tong, thank you very much for accepting our invitation. And you can start your presentation whenever you feel like. We usually have this presentation of around 50 minutes, and then we leave some 10 to 15 minutes for questioning afterwards. Okay?
Thank you. I try to finish within 50 minutes.
Oh, all right.
Yeah, thank you for your kind words, and particularly thank you for inviting me to give or discuss here. For the work mainly by Vincenzo Sessa, my PhD student. She now working in London. So this work supported by the DSTL. So with colleagues Stephen Herring and Tim Ford. So the title is Thermal Stratification Effects on turbulence and dispersion in internal and external band layers. So the two keywords, one is the thermal stratification. So this only has attracted attention in the recent years before people consider the urban flow just neutral. Yeah. The second point is keywords are the internal and external band layer. So why I mention here, because excuse me, in the CFD or particular LES, we use a lot use the periodic boundary condition, and of course this is it's good as in terms of the setup of the model, but in many cases are not realistic. So we develop a turbulence generation as inlet, something like you do this in the wind tunnel, right? So you can see the picture here, right? So you have the turbulence generated, and then you have the flow approaching to the array of buildings, and then you generate something like the internal band layer here, and on top of that is the external band layer. So I'm going to focus on the two keywords today. Sometimes I may skip a bit to keep the time. So first, I try to give you a quick introduction and then some methodology on the LES, and the large-eddy simulation, and the turbulence generations. And then something about the internal band layer. In the neutral stratification, I think it's useful to give you some test of the some feeling of the neutral stratification first, and then I'm going to come to the stable stratification. Yeah, so the validation and the effects, and then I try to close that later. So okay, so what is band layer? So yeah, sorry, so this is a bit overlapped. Assume this is a city like Victoria or London, and you have an approaching band layer, can be ocean or can be a rural band layer, right? So when you're approaching to this band layer, approaching to the edge of the city, you generate the internal band layer here. Yeah, you call the urban band layer here, right? And remember the scale of these things. Yeah, for 1,000 meter we call the neighborhood scale, and 10 kilometer we call this is an urban scale, right? So here we are considering the neighborhood scale only, yeah, with a high resolution to resolve the buildings. Right, okay, so stratification first. This is before the lockdown. We my family take one day off in London, and luckily we took some pictures with this kind of fog. You can see, right? I think this is in a weekly stratification condition, and keep the fogs just. This is city of London, right? On the top of the buildings and the tall buildings. Yeah, this can cause problems, you know. So. And beautiful city, Victoria. I tried to find some pictures. Yeah, so this is 2020 from YouTube. Here you can see in the far field, I found something just on the top of the city because I like Victoria city, beautiful. I spent 2 weeks several years ago. But that picture I have to buy from somewhere else. It cost me £300 and I give up. So this is one, but still you can see, yeah. So if you recognize this is Victoria, right? You can see some mist. This either in the early morning or in the evening. So you can find the thermally stratified band layer on the top of the Victoria city. So you can see beautiful, yeah, the folks, yeah, on here, right? They're quite stable, right? Okay, so this sometimes you can get a really beautiful picture, but sometimes can cause problem on the dispersion, right? So here is a large-eddy simulation in neutral stratification. Just give you a clear, better image of what this kind of internal band layer and external band layer looks like. So you can see the interface between the internal and external band layer, and they interact with each other. Okay, so and the big question we try to ask is whether the thermal stratification will change the height of the interface, for example, right? So this is another point of this talk, of this research. And I have to emphasize at the moment the CFD or a large-eddy simulation can do a good job compared with the wind tunnel scale model. Yeah. So we focus on validation against the wind tunnel at University of Surrey. So this is a Surrey's wind tunnel. You can see 20-meter length, 3.5 meter in width, and 1.5 height. So usually the band layer thickness above this a group of buildings is roughly 1 meter. Okay. So this is the wind tunnel model. If you look the right-hand side, so this is the array of the buildings. So it's nearly 300 blocks, and the block height is 70 millimeter, right? And the incoming speed usually 2 meter. And IE tau, so the real number based on the skin friction velocity is 830, right? And come to the model, CFD model. We didn't do the entire array of the blocks. Rather, we do this smartly to save the cost. So if you use the periodic bound condition, which we still, I mean, in paper, you can find still a lot of paper using the periodic bound condition, which is the red one. That means we assume the flow is fully developed, and the velocity and pressure on the inlet side are exactly same as at outlet side. So this is commonly used, but in many situations might be not realistic. So then we also developed another case, which is used in this research. We use the inflow condition case. This is something try to repeat the wind tunnel. So the domain is something like this size, from here to here. Yeah, and then we focus on this area. Right. Okay, so now you can have a picture of the wind tunnel, and then you can think what at the moment we try to set up a model. You can call it this is a virtual wind tunnel, right? But the good thing for the virtual wind tunnel is you can have a really good control on the turbulence, temperature, these things. Yeah, I can discuss a bit in the wind tunnel. So control the temperature is not so easy in the wind tunnel. Okay, so equations, right? I only have one slide of equation, but I have to give you something, particularly, yeah, some young researcher here. Yeah, so I think it's good to give you something. So we are using a large-eddy simulation only in open form. We tried the Smart-Grinsky model with damping, and we used a sort of dynamic model called mixed time scale model. Okay. And this is a momentum equation in large-eddy simulation. So the only difference is here is the F, which only is non-zero in the vertical direction, which come from the temperature difference effect. So you know the stratification, if you have a lighter air on the top of the boundary, and you have a heavier air and at the bottom, we call it this stable stratification. That means you can kill the turbulence, right? So here we use the Bernoulli assumption, assume the change of the density of the air is very small. They only cause a force in this term, but we keep the density here in the other place are constant. Yeah, so this is called Bernoulli assumption. So you have a small force here, yeah, which for the stable stratification, this force going downwards, which is our study here in this talk. We don't consider the unstable situation in this study because we think this is not a big problem for the dispersion. Actually, the unstable stratification can enhance the mixing and dispersion in urban area. So here we don't consider these cases. Okay, and then we have the scalar equation, which here we consider as a gas or anything like CO2 or whatever. So the modeling is quite standard. So you have the unsteady term, convection term, you have the diffusion term, which include the molecular diffusion coefficient here, and this is a subgrid-scale diffusion. Yeah, and you may have a source somewhere. Right? The temperature equation is almost the same as the scalar equation. Yeah, so you have the molecular diffusion term and have a subgrid-scale diffusion term. The difference compared to that guy, the scalar equation is, so the temperature will have some impact in the momentum equation, yeah, which is on the this term, yeah. Okay, so this, we set up all of this in open form, and we need, for this case, we need the inflow generation code or method. This is developed. This has been developed by me and my colleague, and this is currently widely used in a number of research groups in neutral situation. So the beauty of this method is we assume this is the autocorrelation between in time or in space is exponential. And from that, you can mathematically derive inertia subrange in the spectra, the -5/3. So this is quite lucky. So and this is naturally produced by this exponential correlation function. So and you quite efficient. So to generate the turbulence, you need the turbulence, the rate of stress, you need the mean velocity, you need the integral length scales, yeah, for neutral situation. So the model is something like that, right? So as I said earlier, it's a part of the wind tunnel model. And with the boundary condition R, so we have an inflow condition, which generates the artificial or synthetic turbulence at the inlet, right? Based on this approach. We use a periodic boundary condition on the natural sides, natural boundaries. We have a symmetrical on the top and zero gradient at the outlet. And the number of cells for this case is that 20 million roughly, and the resolution we use 16 point per height. This is quite standard. And the real number based on the height is 12,000. Okay. So just give example what we need. You have the mean flow at the inlet. You have to prescribe this mean flow, mean velocity. You have to give the shear stress and the 3 normal stresses. So if you cannot find the measurement data, you can use a smart way, like use the similarity theory to estimate roughly the turbulence normal stresses and shear stress. Yeah. Also, you need the length scale. The length scale, yeah. So if you don't have any, again, you don't have measurements, you can, based on the previous people's suggestions, for the urban flow, this length scale is roughly the same order of the building size. Like here is H, roughly in the vertical and the span-wise direction. But in the X direction, in the string-wise direction, is roughly yeah, from very small near the wall to 4H. Okay. To do the so this is a neutral data we use to study the neutral conditions, a neutral stratification case. So for the stable stratification case, again, luckily we can get this data from the wind tunnel data. So this is the mean flow in stratification at Richardson number 0.2. And these are turbulence. You can compare with the early slide, just smaller than the neutral case. Yeah. For the temperature, we need again the mean temperature profile over the height. Yeah. So we also need the temperature fluctuations, or you can call it the variance here. So this also, again, we obtained this from the wind tunnel. Yeah, okay. And the besides the real number we mentioned earlier, yeah, everything's fine. Hello.
Yes,
Yes.
Yeah, no, I mean, because I just stare at my screen, looks a bit. I mean, for this, I cannot see any of your face. So, okay, so if you have a problem, shout it to me. Okay, so besides the real number, for the stratification, we need another dimensionless number called Richardson number. Yeah, so here we use bulk Richardson number, which is the reference temperature. So temperature something like at the free stream velocity or free stream flow, and minus the temperature on the ground, and normalized by the free stream velocity, and this thing, blah blah blah. Okay, so in the wind tunnel, the temperature roughly is 10 degrees. The difference, the temperature difference is roughly 12 degrees. And the velocity for this case is smaller than the neutral case because they want to get a higher Richardson number. So it's not easy again, can see, right? The domain height for this is 12H. We have done the neutral and Richardson number at 0.2, which has been done in the wind tunnel. Yeah. And also 0.5, 0.7, 1, And 1 star, I'm going to discuss a bit what the 1 star. Okay, so I have to make this clear due to the data from from wind tunnel. So what we try to do is we only have as I said, we only have data at Richardson number 0.21. So for all the simulations, for example, at 0.5, 0.7, and 1, we use the same temperature variance. We use the same turbulence at the inlet, same integral scale for all the other cases, because we don't have data. But then people argue, okay, for different Richardson number, you may have different inflow turbulence, right? So that's why we have done the 1 star. Yeah, I'll come to this point later. So the again, the configuration is something like that. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, this 12, 13 arrays of blocks. And we have got the upstream is still ruffle of the upstream of the blocks is still ruffle, is 2-dimensional small roughness. So the Y no or the no is 2.3 millimeter, and the roughness over the array of blocks is 5.6 millimeter, right? And also, you can estimate the thermal reference length is that. Okay. In the wind tunnel, they only did the point source, which is S2. Yeah. They will consider in the future to the 9 source. So why we have done 9 source in LES? Because it's much easier for data analysis and for the understanding of physics, because you can think across the span, across the natural direction, they are homogeneous, and then you can use the way to do the natural average. Yeah, so this can give you much better converged small data than the point source data, right? So that's the reason we also done some 9 source simulations here. And you can see the details of the location of the sources. So the 9 sources, 10 H is far enough to the inlet. Yeah, it's almost we think it's converged or developed, fully developed. Yeah, S2 is 13 H is here. Right. Okay. So I show you quickly the neutral stratification data. So this is mainly for validation for you, right? So we compare the turbulence at the we call here, this is short straight. We call this long straight, right? This short straight. Good agreement with the wind tunnel data. Also, we try to compare with the periodic bound condition. You can see periodic condition is not as good compared with the inflow condition data. So I quickly go through. I don't want to repeat that. So then, we try to identify the interface of the internal boundary layer and external boundary layer. Yeah. So from the near inlet to 3H upstream of the leading edge. Yeah, so you can see some. Yeah, so this is a profile we give. And then you come to 1.5H downstream of the leading edge of the array. Leading edge is the edge of the entire array of the blocks, right? So now you can see. Remember, this is Y over H with power 0.25. So this gives you a better way to show this the interface and this mean flow. So you can see the interface downstream is something like that. Yeah. So it's clearly there is an interface, and people before try to parameterize or fit a function like that or this. And if you use the vertical turbulence variance, sometimes you find it may be easier to identify the interface between the internal and external boundary layer. So from here to here, right? Okay. And this Vincenzo tried to fit this profile, to fit this interface is something like this. Okay, so and you can see this compare with other methods. They are quite the interface is quite close with each other, right? Okay, so I skip this. Given time, I want to discuss a bit more on the stratification case. The point I would like to make in the neutral stratification, we have a good agreement with the measurements, particularly compared to the periodic bound condition. Okay. Right. So maybe I can give one point for the neutral stratification. So the point is the use of the vertical rate of stress approach was found to be a tentative method which enabled the location of the internal boundary layer interface to be more clearly defined compared to use the method of mean velocity and the string-wise rate of stress. Okay, so this is my point. I have 20 minutes to go. Right, I try to make sensible chart here. For the validation first. So sorry, they have done an intensive study on the Richardson number 0.21. So and we validate the mean flow temperature difference, the vertical, the string-wise fluctuation, vertical fluctuation, and the mean concentration at 1.75 H from the source. So they are quite good. They are quite good, right? We have a small difference. The point is again compared to the line source, the point source data is quite is entirely 3D. So yeah, so it is a question: how can you get a longer time for average? Yeah, so we have some difference here. So this still is can be is an open question. So the another question I would like to discuss here is the difficulties or uncertainties in the wind tunnel on the measurements of the temperature on the ground. So it's hard to get accurate. Actually, you don't have accurate temperature on the surface, right? Because in reality, the surface, the ground is quite complicated in theory, right? So they give one estimation on one curve, right? So the solid line, yeah. So another one, so this one, yeah. So one is we based on the wind tunnel work is 12 degrees, 12K difference. Another one we try to assume there is a 2-degree uncertainties on the temperature on the of the ground of the flow of the wind tunnel. So add 2-degree difference here on the ground, yeah, and then we try to assess the difference in the output in the final results. Okay. So now you can see from the results, you can hardly see, yeah, for the mean velocity, the mean concentration, yeah, they're quite small, right? And yes, the temperature, the vertical variance, and the string-wise variance, yeah, they're quite small and shear stress. So why it's so small? And then we try to understand. So if you consider the incoming heat flux, which is the the heat flux from the mean quantities U and T, right? And the turbulence flux. Usually in the streamward direction, this is very small. Yeah, I mean, we have a joint paper with you guys, right? So we found that this is quite small. But remember, near the ground, the U is almost 0. So that means this mean quantities is also very small, regardless you have a 2-degree difference. So overall, the small difference on the ground, the small difference temperature on the ground make a very little difference. So this is a good point. So we don't need to worry of the small uncertainties in the wind tunnel test. Another point is the turbulence data at the inlet. So most of the data we use, most of the turbulence data we use at the inlet, except for RA equal 1 star, are the same as for Richardson number at 0.21, which is also measured in the wind tunnel. Right? But people will think, okay, so in different Richardson number, different stratification cases, situation, the turbulence might be different. Okay, in reality, they are different, right? So we try to do something more. So what we did from the observation or previous work on also including Surrey, they found there is a constant ratio of the TKE over the skin friction velocity, yeah, in weakly stratified flow, yeah. So this ratio is more or less similar, right? More or the same. And Surrey have tried to measure the U star, estimate U star somehow, right? And then if we plot this in log scale, you can see the U star is decay more or less exponentially as the Richardson number, yeah. And then at the Richardson number 1, we can estimate U star is this value, somewhere, yeah, 0.3 something. Based on that, we can estimate the TKE and the turbulence shear stress, turbulence normal stress, like these things. And then we can generate the turbulence at the inlet for Richardson number at 1. So for the Richardson number at 1, we have 2 sets of data. One is based on this estimation. Another one is use the turbulence just from the Richardson number at 0.21. Okay. Right. Okay. So there are lots of interesting data, but I try to emphasize today is the impact. Yeah, the impact. Because the major point is before think, we can forget the weakly stratification in urban area because the momentum is big. The momentum force is big, and the Richardson number is small, and then it's the stratification is small. Yeah, but here we can find they are different, and this is a different story. Okay, so here is the show the Q criteria at different stratification. Remember for this 1, 2, 3, 4, and the incoming turbulence are the same. Yeah. So so this is the vertical plane across the buildings, actually at the central plane of the buildings, over the buildings. Yeah. Yeah. So 2 points. 2 points here. So first, you can see the internal and external boundary layer interface. It's shallow, much shallow. It's much lower than the at higher stratification than the low stratification. Yeah, this is very obvious, right? Also, you can find at larger stratification, the turbulence are getting weaker or decaying. Yeah, decaying fast. Yeah, right. And also there's more detailed data for the interface height, the height of the interface, and based on the vertical fluctuation, right? Okay. So these are at a different location. Yeah. So let's focus on one. And so this is on the 18H from the inlet. Okay. So if you look the neutral stratification, the interface between the internal boundary layer and external boundary layer is here, is higher. Yeah. And then we will use the Richardson number 0.2. They're closer to here, but slightly lower. And then if you increase the stratification, giving the incoming turbulence still the same as the Richardson number 0.2, they still can see there is an evident change of the boundary layer height, the internal boundary layer height. Yeah, going down here, right? So this 1, 2, 3, 4 use the same inlet turbulence conditions. And then the last one, the Richardson number 1 star, we use an estimate lower turbulence at the inlet, and then you can see there is a further decay compared to the same stratification but higher turbulence. Okay, so this gives you some estimation on the using the same turbulence fluctuation at the inlet, but for different stratification, can give you something reasonable, but perhaps it's a bit overestimated than it should be. Okay. The big point is the stratification on the mean flow on the internal boundary layer height impact is very evident. Yeah, can be significant. Right. Okay. This similar thing. Right. So you can see the boundary layer height developed, the internal boundary layer height developed over the streamwise direction at a different Richardson number. Yeah. So there is a clear tendency when you increase stratification, the internal boundary layer thickness or the interface height going down. Yeah. If you reduce the turbulence or TKE, turbulent intensity at the inlet, you reduce the boundary layer, the internal boundary layer thickness further, right? Like this. Right. Okay. So then we decide to have a more rigorous or controlled simulation of the dispersion in the stratification situation. So then we place a 9 source here, right, at the 10H. Okay. And again, so we have two row of the controls. This is the concentration. This is concentration. This is instantaneous data. So at the stratification from the weak to stronger, even stronger, we can still consider this is a weak stratification. Yeah, you can see there's a big difference, right? The plume height is smaller than the in the stronger stratification than the weaker stratification. Excuse me. So this is the plane cross the building, at the center of the building, and this is the plane cross the short street. Yeah. Clearly, you can see if you compare the first one against the bottom one, yeah, the picture is quite different. Yeah. Remember, for the 4 cases, we have the same turbulence level of TKE at the inlet. Okay, here is some it's movie. Yeah, I only show one movie in this talk, so yeah, cause it takes time. So this is the weak Richardson number 0.2, and this is a stronger Richardson number 1. Yeah, and the source is the line source here. It is the first blue area. You can clearly see, right? So the plume tracked more. Yeah, I don't move this mouse to here. The plume, the concentration are trapped more in the second case than in the first case. Yeah, the first point the clearly is very clear. Secondly, the first one has a higher plume height. Yeah. Okay. And then you think of what's happening to the concentration. Okay, so what we do, we try to average the concentration over the so for example here is from the from ground to building height. Okay, over different streamline location, yeah, at a different Richardson number, okay? And this is streamwise total flux. This is the flux cross the vertical plane within the canopy. And this flux cross the vertical plane from the ground to 2H, okay? And you can see they're shocking, right? At higher Richardson number, you can see the concentration, the scalar. Most of scalar goes through within the canopy, right? So you can hear, right, within the canopy. Yeah, if you look at a slightly higher at 2H, almost 100% goes through this height. That means nothing go outside of 2H. Yeah, for Richardson number 1 and even 0.7, right? 0.7 is 0 is here, right? So this gives you a very strong indication of the dispersion. Okay, and we have more to look into the plot in different way, but I don't want to show more. I need to have more time to discuss with you, right? So here is a vertical profile at the center of each non-street. For example, here, right, this is one, this is the first one, and then go to the second one. So this is different location on the non-street, yeah, on the non-street. But span is average cross the natural direction, cross the span. Okay, that means we can get a smoother data to understand the stratification. Okay, so if you look pick up any location, let's do this one. So this is 8H, right? It's 8H to the source. Yeah, 8H somewhere 1, 2, 3, somewhere here, right? Somewhere here. Okay, so you can see, yeah, there are lots of information here. The neutral one is low concentration, but higher concentration above some height. Yeah, and then you come to the Richardson number 0.2, is a solid one. Yeah, and then all the way to Richardson number 1. But remember, all of this data in stratification, we prescribe the same turbulence. So if we include the RA equals 1 star, is further somewhere here, right? So you can see from here to here is doubled or more, right? It's really substantial, right? Okay, so before I go to the conclusion, is in the real situation, the like now in London, right? The Richardson number can be much higher than 1. Yeah, and for this Richardson number, actually in the wind tunnel also cannot deal with it. because they have the limit of temperature, right? So then from here we can understand in the real situation the thermal stratification can make even bigger impact to the turbulence, to the structure of the boundary layer, and to the dispersion. So at least I can say the impact of weakening thermal stratification, I equal less than 1, and flow, turbulence, and dispersion is evident, right? So the point is that the impact of even a weakly thermal stratification on the ground effect dispersion is definitely not negligible. Okay, so I stop here. So I just mentioned one sentence here. So the measurement data come from this paper, and Wen Qingzhou published 2 papers. If you want to go to read the neutral one, is on the Journal of Wind Engineering and Industry Aerodynamics, and the thermal stratification is a boundary layer metrology. Right. Okay, I stop here. Thank you.
Thank you very much, Tong. It was a great presentation. Yeah, very, very helpful for us. That we are working with this at the moment. We have 2 students, 2 postgraduate students working on that. One under my supervision, and the other one under Elisa's supervision. So I think your presentation is going to be very, very helpful for us. In fact, we would like you to collaborate with us, like we did with Victor dissertation. I think it would be a pleasure for us to do it. We are working, well, for us in Brazil, unstable stratification conditions, they are quite important. So we are very much interested on that. But, well, I'm sure that some of you have some questions. So I have a few of mine here written in this. But before I do that, let me forward to the audience. Do you have any questions that you would like to ask Professor Zheng-Tong? No?
Yeah,
so, yeah, they're a bit shy, but I have a few here. One of the things that when you showed the mesh, I was a little bit intrigued with that, because you use a uniform mesh then, right?
Yeah.
Okay. Yeah.
For this one.
Yeah.
Uniform mesh.
In Victor, we use that non-uniform mesh because we wanted to get the flux right in the very close to the surface, right? And you notice, you show one of your slides when you have the agreement of the periodical simulation. It's not as good as the one with, well, when you have the development of the boundary layer. Why you think was that? Because perhaps it was too close to the beginning of the blocks?
Yeah, okay, so perhaps yeah, you can share the screen here. Yes. The point is yeah, let me to some people may be not able to remember what I really showed. Yeah. For example, here, right? This one.
Yeah, that one.
Yeah. So the solid line is a periodic boundary condition, which assume the inlet and outlet turbulence are identical, right? It's something like a recycle or something.
Yeah.
Yeah. And this is the dashed line is the inflow condition, and the symbol are from the wind tunnel. Yeah. So I mean, this is not, it's mainly investigated by Vladimir Foucault before. Now he's in Czechia. The understanding is for the periodic boundary condition is actually we assume the number of the array, the number of the blocks is infinity. It's mini itself. Yeah. That means you can have a thicker boundary layer.
I see.
Well, in wind tunnel, again, they're similar, like also in Victoria, right, or London. You never have an infinity number of the buildings, right? Yeah, particularly in the like a city in Victoria, you immediately for 10 blocks you come to the coast. Yeah, so the turbulence is not as the periodic. That means you have a less turbulence here. That's the argument we need to use the inflow condition.
I see. I see.
Yeah.
So this data that you are showing is the averaged over a short straight, the velocity profile of a short straight, right?
Yeah. So this is on one point here. Yeah. So yeah, it's here.
How far away from the beginning of the buildings, the building array? You remember that?
Yeah. So no, I don't remember, but we know here you must be. I mean, some people publish some paper, the American writing name, and you have to be careful. At least 8 h from the leading edge of the array.
Great.
I don't remember exactly, but you can see what we focus on is these areas. So the 8H and 10H at least.
Okay. Okay.
Yeah.
So even at 10H, you get some difference from, well, using the entire domain and using a periodical boundary condition. Then.
Yeah, because in reality, if you look somewhere here, I think we have something. Yeah. So the flow, I mean, in reality, we consider maybe at 10H or something, 15H, we assume they are converged, but they're still slightly growing.
I see.
Particular turbulence, right? In wind tunnel also because the cost, right? So, so even you're given this wind tunnel size, right? They're not exact same as a periodic because still is quite a limited number of array of blocks.
Yeah, I was wondering that because one of the cases that they did simulating the wind tunnel is the 45 degrees, right?
Yeah. So So no, I'm not say anything for the 45 degree. We have not published yet. Yeah. So I mean, this is more interesting. It's actually hard also because if you do wind 45 degree, the wind. Can you see my mouse?
Yes.
Yeah. So the big trouble is where is the leading edge because flow come here, right? And they try to cut something like that, and then so so I mean, Wenqingzi have done a number of simulations, but we have not have time to tidy up this data to publish it.
Yeah. So you tried the 45 degrees as well.
Yeah. I mean, we have a lot of cases.
I think it's going to be a very challenging simulation.
That's right. Yeah. Challenging in terms of the wind tunnel and the CFD. For example, for here, and they use the turning table, right?
Yeah.
Yeah. So what they do, if you see from the right, the wind just comes something like that from the corner, right? That means at a different location, you have a different distance to the leading edge. Yeah.
That's true.
Yeah. I mean, for example, here, if you wind come 45 degree, 1 point here compared to measure if you have a measurement cross here, right? So data here, of course, you cannot trust, right? Because too close to the leading edge.
Yeah.
That's what I'm saying. The wind come from the 45 degree.
Yes.
And that means you have interaction from very close distance to the leading edge. For example, this point.
You have to do it periodical, right?
What we did is we did both. I mean, particularly focus on the inflow condition also, right?
Oh, you did.
Yeah. So we can have another talk here. For this.
we can arrange that. Yeah, that's quite interesting, really. Well, we'll have a lot of questions about it because it's a difficult problem to solve it, isn't it? I was wondering, I wrote here in this piece of paper some questions. Well, how about the boundary conditions? I mean, especially in the floor, right? You use you specify the temperature, right? Like they did in the wind tunnel, or the flux.
Okay, very good question, right? I mean, flux is not a problem. Yeah, so flux, we don't release the flux on the ground, and neither in the wind tunnel, right? So the flux on the ground is zero gradient. That means you don't have any flux go inside the building or on the floor, right? Okay. So this is usual case, usual boundary condition. Normally people use that boundary condition. You don't have flux go inside the building, right? Yeah.
Okay. Yeah.
The trouble is, I don't see the trouble. The tricky thing is temperature. Yeah. So temperature, of course, in reality, you're building and the ground, you observe temperature, right? So or you release temperature, right, due to the radiation, right? So you from sun, every building release temperature, release the heat. Okay. So but in wind tunnel, it's very, very difficult, right? How can you heat every building, right? So what they're going to do, they may heat one building or several buildings, or suck the temperature or energy into the building, right? This is enormously expensive. Yeah. Similar as in the CFD. So if you want to have a good prediction on temperature, we published a paper, right, with Victoria or with Victor, right? So if you want to have a good prediction on the flux on the surface of buildings, you need a very high resolution.
Yeah. So you actually in the simulations you specify the temperature in the ground, and the buildings are considered isolated.
No, they're all the ground and building are isolated.
Okay. So you have only the stratification that is coming from the inlet.
Yeah, only from the inlet. Yeah.
Okay.
Yeah. This stand assume you can check, right? So the air pass through the buildings in 1 second or something, all the building, right? So the area here is so it's 2 meter or something. The speed is so it's fast enough. We assume the impact is small.
Okay, and in that case, that you use periodical boundary condition, right? How periodic boundary condition? How do you get this temperature stratification? Because I thought that when you were explaining, I thought that you had this temperature in the ground, right, and the ground, and then in this periodic boundary condition, then the stratification just developed in inside the domain, but it's not that, or is it?
No, we didn't do the stratification in periodic condition.
Okay.
Yeah. But we published 1 or 2 papers by Bratti, use periodic boundary condition with 4 blocks, and we have to use at least 64 points per edge, and we also check the 128 point per edge.
Yeah, like we did with Victor, we need to have a very, very fine a mesh close to the surface, right?
Yeah, that's the point. Particularly if you specify the constant temperature.
I see. Yeah. So if you go if we specify the heat flux, for instance, we don't need to do that. But if you have temperature, then we need to have a very, very fine grid close to the surface, right?
Yes, something, like that. So I mean, that's right. I mean, in terms of if you want to have a good prediction of the flux over the city, so the best way is to give the flux boundary condition on the ground. So at least you don't have the global flux too different from reality, right?
I see.
But temperature maybe have some errors, big errors.
Right.
Yeah, because it's based on local law and something, right? So the trouble is the flux can make a non-distance impact. So if you give a temperature on the ground and if flux is not right, that means globally it may be totally different story. Yeah. So
we need to be careful with that, isn't it? Elisa, you want to comment something?
Actually, I want to ask you something related to that, because I think the wind tunnel hits the air in the before coming to the tunnel. Is it right?
Say again, Elisa. I cannot get you.
How the wind tunnel hit the air? Is it before everything, before coming to the section?
Right.
So they have the profile, the temperature profile.
So the wind tunnel, what they did is they have, I don't remember how many layers at the inlet. So they have different heater, 13 or something, to get a temperature profile at the inlet.
And then that's it. And then the flow
No,
develops.
Not yet, right? So and then they cool down the flow by water.
Oh, they have panels in the floor.
The panels on the floor, right?
Okay.
Particularly upstream of the buildings, yeah. And they can also heat.
Okay, they can make. Okay, so there's a temperature profile in the beginning, and then the surface is cooled, and then you can make it stable. Because I didn't understand how is it compared from the earlier simulation with the wind tunnel. I didn't get it. The similarity of the.
So they did is that they of course they cool down the air upstream of the array, but not in the array.
Not in the array. That I get it.
Yeah. So they try to get. I mean, you have to use like the turbulent generation, right? Similar. You have to use the shock teeth, the vortex generator at the inlet, and with the roughness underground. So the two things, when going down, they interact and reach somehow a converged band layer.
I see.
Okay.
Similar temperature. So they produce something, try to make it as close as possible. It's really hard because you only have a certain level of the heater, right, or something, and you generate a profile, temperature profile, right? High temperature, low pressure, and low temperature at the ground, near ground, and then also use this heat or cooling to adjust it.
Okay.
Remember, from the inlet to the array is quite a long distance.
Yes, I remember that.
Yeah, so you have to adjust it.
Okay, so the flow that's going over the array, that's a profile, and then the stability, it's stable. That's the turbulence, it's stable. And then you're comparing with your simulation. So everything it's not changing temperature, not changing heat, the ground and the building. And you're coming also with a temperature profile. That's correct.
Okay, so maybe I didn't make it very clear, right? So what we do, we take data. I mean, also they take at 3H roughly upstream of the array, the leading edge of the array. They think the temperature and turbulence are converged and not change.
Okay.
Yeah. So upstream of the data of the array, we think this is our inlet.
I see.
We're not able to produce the inlet all the way to the real inlet on wind tunnel. Somebody in Norway, they use my inflow generation, also similar to do that exactly, but the cost to model the upstream of the building is something 10 times bigger something than the array itself. If you try to model everything in the wind tunnel.
I see.
So what we do, we take data something 3H upstream of the array, the inflow condition or the inflow turbulence. And in reality, they don't hit the turbulence, the ground in the array in the wind tunnel. So this is quite matched. We need to check, right? We need to check then we have done quite a lot of this, and we need to check, for example, after the something like 10H from the leading edge, whether they matched with the wind tunnel. Yeah, so this is our first check, whether they're the same as the wind tunnel, so they're close.
Okay, I think I got it. Cool.
That's great. Well, I see that we are going to 11, nearly 11:10. We passed a little bit the limit, but anyway, I think it's very, very useful because we're all learning a lot with your experience. I'd like to thank you again for the great presentation and all your work. And I'm sure that me and Elisa and the students involved in this work will need to have a further meeting with you just to discuss the details, because we could spend the entire afternoon here talking about it, because there are so much difficulty, so many difficulties involved in this kind of simulations. And I think it will be very, very useful to talk again with you about this subject, isn't it?
Yeah, so I think this, it's good. I did give you something, a favor, right? I mean, read paper is hard also. So give you something, right? And then, so to form a collaboration or something, we sit down. I mean, nowadays, the online chatting is very useful. I don't need to fly to Brazil. You don't need to fly.
No.
Yeah, it's true. This was one of the very good things that we learned in this COVID situation, isn't it? We are learning to work with this video conferencing, and we are collaborating. I think collaboration is easier, isn't it?
Yes, I mean, in that sense, it's cheaper, right? Efficient. Yeah,
it's true. It's true. So, Elisa, you want to compliment, say anything?
Oh, I just love this talk. I'm just thinking, because I think we need to adjust something that we are thinking before. So thanks very much. It was really, really good. I had a lot of fun watching.
Yeah. I mean, so Elisa, what I can say? What I can say, right? So this is open forum, so I'm really happy to share the for example, the neutral one, the text back. Have you used that before, right? I don't remember now. So you can
no, you don't use open but something that we are always thinking that should be in our to-do list. We should do that.
Yeah, so you may think of that, because one of my student, Kuti, she now is working open forum. They provide a number of surveys or something, and she implemented also the temperature fluctuation code on behalf of DSTL into the open forum official release. I think maybe you guys can consider use open forum, because you don't need to pay the license, and you can use a big number of codes, right? The only thing you need a bit more time to kick off. Otherwise, it's better than Fluent.
Yeah.
Yes, we should do that.
Yeah, one of my students is starting working on that. Yosimar Elisa is working on that. So we have already installed in the machine, and one of the students is learning. It's a good thing. It's a project like that one you did over Southampton, when you have this wharf simulations, the mesoscale model, and then you simulate LAS inside the city, right? It's a project more or less similar to that. We are not using LAS inside the city. We are using K omega inside the city, but it's more or less the same project, and we are trying to do with OpenFOAM. That will be our first try with OpenFOAM. I think we are learning. We are learning.
Yeah. Okay. I mean, Level, you reminded me now. So Xiaoming Kai, in Birmingham, he had one postdoc implement the turbulence, inflow turbulence in WRF, and it's free. So I can get the link to you and the paper. So because I think this journal is geography or something. Ask the code must be open. Okay. So you may think of use it's LES, right? So it's a WRF. Yeah, maybe you can continue, right?
No, that will be very nice. Yeah. And well, this is another presentation that you can do later, isn't it? Because it's very similar to what we are trying to do. So, but okay, we're not going to abuse you. We wait a little bit, and then you can come back later.
Yeah, I mean, it's good to have, I mean, to more like this kind of chart, more productive.
Yes.
Yeah. So
Yeah. That's very
maybe
good.
I need. I think I need maybe one day to
Process
organize
of it.
everything, just to process everything, because I think we need to change something.
Yeah, the way that you're doing a few things. Yeah. It's good.
So
And
maybe
then,
we can have another meeting, just us.
yeah. We can have this meeting, and then we can talk to Tong as well. And well, we start the collaboration. I'm sure that Tong has a lot to contribute in this work. I'm quite sure. So it's going to have another joint publication in this. So anyway, thank you very much, Tong, for being here, and then thank everybody for attending. We have a lot of people in the YouTube channel as well. I apologize for those of you who tried to get in the conference room, but we're trying to obey the regulations of the university, and we try to limit the access to people with the university login account. And then most of you that tried to access with a private emails, we were not able to get in. So we watched via YouTube. We have quite a lot at the moment. We have nearly 20 people watching at some moment in the YouTube. And well, in here we got 17 or so. So quite a good attendance for such a highly specialized presentation, isn't it? Yeah. So again, thank you very much for your time. Thank you very much for your presentation. All the best to you. So take care, you and everybody. See you soon, I hope.
Yeah. See you soon, I hope. It was really good to see you. Bye.
Yeah. Bye-bye.